In the cooling group, we were mostly focused on photo-induced processes and semiconductors. So shine light on a material and they create an electron in a hole. Then we try to describe the dynamics of those charge carriers in general. And specifically, for my thesis work, I've been focusing on lead halide perovskites as a semiconductor because they've become emergent in the energy community because they show great quantum yields and photovoltaic efficiencies. And a lot of the peculiar properties of charge carriers in lead halide perovskites has been attributed to polaron formation in these materials. So as to describe polaron formation, so you imagine, so this is our lead halide perovskite model. And so those are the sticking balls, and then these different colors, they represent charge. So you put a charge into the box, and then due to these materials being soft, there's a lot of nuclear reorganization. And so, and due to the change in the coordinates of the ions, the charge becomes self-trapped, known as a polaron. And polaron is like a quasi-particle, so it's like other quasi-particles that have internal excited states. So you can imagine that this charge in here is bound by a Coulomb potential well, and it has different excited states within that well. And essentially what we were trying to do with this work is to look at the optical spectra of these transitions and then model the excited state dynamics, considering if you can get a hot polaron, then look at its radiative and non-radiative pathways in our atomistic model. And so the first work we did on this was on individual polarons, so either having just a positive charge or a negative charge, so adding or removing electrons.
When I focus, I probably can answer it myself, but it's with quite of memory. What in the first schematic diagram of this hydrogen-like thing, what is the definition of R and how does it differ with Cartesian coordinates of electrons at the left panel? Is it the same scale, or R is infinitesimal change of atomic elongations, like left and right panel at the bottom of the introduction? What is the length scale? Is it exactly the same, or is it completely different?
I would say different. So it's not bond length necessarily, it's reaction coordinate. So I guess what I would say is, so like a charge has a natural size, but then due to polaron formation or ions moving, it traps the charge, so it's kind of shrinks it down. Smaller than its normal, or than its natural length.
But this visual appearance of this length scale of the blue box and the vector R that look visually the same doesn't mean that they mean the same thing. It's a deceptive impression.
Yeah, so it's not one for one. So like this length and this length aren't necessarily the same.
Okay, then maybe one can put in the blue box another vector with R lowercase. So it's a different coordinate. Anytime I open the poster, it's like big temptation to be able to do this.
I mean, in principle, it could be like if instead of these green parts coming out to the very edge, they were shrunk to just the inside of the cube, then it would be like a one-for-one comparison. But in this case, our box is just too small. So that's kind of the introduction. So,
and what was the challenge?
The challenge? So I guess the challenging parts of describing these is the radiative and non-radiative relaxation, because to do polaron formation is just using commercial software and just extracting the data correct. But to do the radiative and non-radiative dynamics, you have to be able to process or further process the outputs into couplings, which I'll get to. So the challenge is describing the radiative and non-radiative parts. And yeah, I guess I forgot to mention the most provocative thing that we tried to model is polaron photoluminescence, and to measure its efficient, whether it could be an efficient emitter, because it's suspected these energy gaps are in the IR range. So if you can get an efficient IR emitter from the polaron, that would be an interesting potential application for these. And so that's the introduction. So this is an overview of the methods, which I won't highlight very much, but use that software. And then we screen for the optimizations, PbTe functionals, and HSE, or hybrid functionals. Just show that even though PbTe is generally less accurate, better qualitative trends will hold. And so since we're dealing with lead states or lead p orbitals, we have to include spin orbit coupling in the calculations. We do that using relativistic corrections. And so this is just an overview of how we compute the polaron states in our atomistic model. And then the most competitive, or the biggest thing that we have to extract is how to get the describe electron-phonon interactions. So you can break them into two terms. So there's the, I guess in our equation, when the ends are the same indices, that describes just nuclear reorganization. So that's how polaron forms in our structure. And then for when you're dealing with not the same bands, those are described by the non-adiabatic transitions. So we cover both of those in this project. And so just kind of a flow chart to illustrate how we process the models. So for each model, there's an equilibrium number of charges, and then so that would be adding or removing 0 charges, whereas to induce polaron formation, we either add or remove charges. So we start with our model, we consider how charged that we want our polaron, and then choose the charge state, put it into DFT, and then for each charge, there'll be a specific change in the nuclear coordinates. So we use delta R's. And to interpret our excited state dynamics, you could there's 2 potential cases. So it's either you have a hot carrier and the lattice reorganizes quick enough, like it won't dissipate any of its energy, whereas if the other case would be that it cools faster than the lattice reorganizes. So those would be 2 different physical situations. But the way that we set up our dynamics is to have a hot polaron and model its non-radiative relaxation. So that's how we attempt to model all of these observables. And so if you're talking about polaron formation, you'd expect changes in the nuclear coordinates for each charge. So that's what are plotted here. So these are radial distribution functions, which describe coordinations between the lead and the bromine. So, which is illustrated here. So it's these A peaks are lead to bromine. Coordination distances in this B is interbromine to bromine. And The big thing that we noticed with these is that for each charge, you would only see changes in one of those pair coordinations. So for the positive polaron, there wasn't a big change in the lead-bromine bond, but the coordination between bromines became narrower. Whereas with the negative polaron, we saw the opposite case, where we saw bond elongation for the bromines, our lead bromines, while there's essentially no change in the bromine-bromine coordinations. And to describe that, we just used a simple oxidation reduction type of framework. So you add an electron, that's going to slightly reduce the lead, because that's where most of the charge density is. So instead of being 2+, it'll be like 1 point something. So it has less strength, or less ionic bonding strength to the bromine. So they just repel a little bit, and then you can do the same rationalization where if you put it in a hole, the bromines become less negatively charged, so they have less interaction with each other. And so just to preface, if you include positive and negative into the same model, you see two different types of reactions from both of them, so which we'll get to eventually. So these are changes in the nuclear coordinates. And so from those new geometries, we can look at density of states and absorption spectra for each of these models. So for each positive and negative polaron, we screen different spin multiplicities, so singlet, doublet, triplet. And in these figures, so for the positive polaron, this black color indicates a hole for each of these. And then these labels just help indicate the optical transitions that we see for IR spectra. And what we notice is that these transitions, they're generally of the same energy transitions, but we see changes in intensity based on the spin multiplicity. So for the positive polaron, we see that the singlet or triplet is generally brighter than the doublet. And we see that same trend with the negative polaron. So essentially the lowest energy transitions are brighter for the triplet and the singlet compared to the doublet. And just to compare, one little cross study is comparing the density states and spectra between PbTe functional and hybrid functional. So you see the density of states there's some swapping over to the peaks, but they're generally in the same spot. So there's not a big difference in the density of states. I didn't plot the absorption spectra, but essentially it just looks like the gap's a little bigger, which is what you'd expect for when you do a hybrid functional. So the big takeaway from this is that singlets and triplets are brighter than doublets. And so when we do our excited state dynamics, we focus mostly on singlet and triplets rather than the doublets. So how do we do our dynamics? So generally to couple electronic and nuclear degrees of freedom, we run ab initio molecular dynamics for each state. So that's visualized with this figure, which is upside down. But essentially, due to static electron-photon interactions, you get fluctuations of the bands. And then essentially those frequencies are for the normal mode that the electronic states couple to. If you extract those, we compute non-adiabatic couplings in our spinner basis along the trajectory, and then just doing correlation functions and Fourier transforms, we can convert those into rates of transitions between each of those states, and those are visualized here, which we call our Redfield tensors. So essentially, the intensity of the peak is the rate for how fast the transitions are between two different bands. And so X and Y is just state to states. So diagonals are 0, and then states slightly off the diagonal should be higher intensity, and it decreases the further away you get from the main diagonal. And The main takeaway from this figure is that the intensities and like the width away from the main diagonal is narrower for the negative polaron compared to the positive polaron. So that's an indication that during the hot dynamics, the positive polaron will cool quicker or interacts more strongly with the lattice than the negative polaron. So it should cool quicker and it should have faster non-radiative recombination. So that's the expectation when we run the actual simulations. So we give it an initial condition and then we just run the dynamics based on these rates. And so what's shown here is you have a hot electron or hot polaron, and it cools to what we call this P state in the polaron potential well.
Please remember where you were planning to go because it will be a certain provocative question. It's not for me, it's for answering the viewers who will be visiting. Why electron-hole interaction is neglected and how much does one sacrifice by not doing true excited state, not doing PbTe or GW collections?
It's expensive.
Yes, everyone will buy, but is it expected that correction will be like doubling if we reducing transition energies 2 times and drastically changing oscillator strengths, or it will be just little quantitative corrections?
Well, I guess this model is you're dealing with individual polarons. So it's just a negative, so it's just one charge, so there's no like other free charge that it's interacting.
But in your storage diagrams, you're the excited for the orange and blue interact. They not necessarily share the same space, and even if they do share the same space, it's like overall charge system, and then you promote your charged particle to a different orbital. There should be interaction between this excitation and the orbital where you're speaking.
So it's not a hole, but it's
Panel. What if I'm going to do PbTe for the state? What would maybe you could see literature for same materials or different materials where one estimates the good distance. Another thing, the interaction between any of the set of interactions, as already covered here, is compensated by the constant. This interaction is less than more rigid materials. It's fun to think that would be outcomes of the discussion because it's like about 80% that's happening.
Yeah, I'm not sure what the binding energy would be, because that would change energy transition energy and oscillator strength would be a little underestimated. But qualitatively, that's what I would expect. Order of magnitude. Sure what it would be?
Yes, we're interrupting. Please keep going.
So yeah, we have initial condition, and then it cools to these P bands, or in the polaron literature they call them relaxed two-sided state. And so we do that for both the negative and the positive polaron, and they show contrasting mechanism or decay kinetics. So for the negative, it shows the bi-exponential decay, which is on a slightly longer time scale than the positive, which is thought was closely a single relaxation, and is generally a little bit quicker than the negative polaron. So just screening through a bunch of initial conditions, which you can plot as dissipation energy, and we can track how long it takes for this relaxation to happen. And what we notice is if you do the same calculations without the polaron geometry, we see that the polaron cooling time is on a longer time scale than like your free carrier geometries. So that's kind of what you'd expect from the polaron geometry, since they should screen phonon interactions more, so they should take longer to cool. So that's just kind of a confirmation that our methodology is working as expected. And so it's the non-radiative relaxation in the excited state. But you can also look at radiative recombinations in the excited state. So along the same trajectory, you can plot the oscillator strength at each time step, and then look at how likely it is to emit a photon. And that's what these plots show. There's time resolved. So essentially you have a hot carrier, and it cools to the band edge and gives photoluminescence, which we call as P to S state. And you do that for both the negative and the positive polaron. And what we see is that the negative polaron is more intense, or the higher intensity compared to the negative polaron. But to get an idea of how efficient it is, we can compute a theoretical quantum yield by just taking the radiative rates, the lowest energy transition over some radiative and non-radiative. What we find when we do that for all the models investigated is that the efficiency is fairly low for all the models, so it's on the order of 10 to the negative 8 to 10 to the negative 4. And what we noticed, something interesting, is that 3 of the models showed about the same order of magnitude relaxation or non-radiative time, but 1 showed 2 orders magnitude slower. And while each of them had within about the same radiative recombination. So essentially we tried to figure out what was so different about this negative singlet model compared to all the other ones that we screened. And so what we did is try to hunt for resonances between electronic optical transitions and vibrational modes. So this figure here describes the normal modes associated with the model, or so these are the normal mode vibrations, and then this is the optical spectra shown earlier for the negative and the positive polaron. And what we did is we tried to look for peaks of the normal modes that correspond to peaks in the IR spectrum. So if they're roughly equal, they're in resonance, so it should be a quick decay. And what we find is that for this negative singlet, it's in resonance with an ammonium that's on the surface, whereas for the other models, they're essentially in resonance with carboxylic acids that are on the surface. And if you plot a partial density of states, you'll find that these carboxylic groups, they bond to the surface. So we call them active modes, since they can contribute, since their vibrations will couple to the electronic. Whereas where these ammonium groups, they're fizz absorbed, so they don't provide direct contribution, so they're spectator modes. So this resonance doesn't actually provide anything to the non-radiative, whereas for this triplet, it's in resonance with the stretching group on the surface. So that's kind of how we explain this two-order magnitude difference. One's in resonance while the other is in physics, so it has a longer lifetime. And so that's essentially the story for the first part of this research that's been published in JPCC. So the takeaway message is you can, using our mixed quantum classical methodology, we can get reasonable results for polarons in these systems, and that even though polarons are expected to screen phonons as part of the ionic crystal, if you have normal modes from the surface, from like interfaces, that those are going to impact the excited state dynamics as well. So for rational control of these materials, you have to consider that. Because a lot of popular materials are based on like very thin films, so it's 1 or 2, 3 lattice spacing, or other nanomaterials which are very small. So the surface will contribute these materials as well. And so that was essentially one project in itself. But the ultimate goal that we had in mind when starting this is that in reality, for all these materials are used, they're photoexcited. So you have both positive and negative charges, polarons in the same material at the same time. And so that's illustrated here. So as before, there was only one charge that provided for the whole positive throughout the whole crystal. Whereas if you put in a positive and a negative charge, so that you're going to have different regions of positive density and negative density in the same crystal. So that's illustrated here. So the blue is weighted by the electron density, which is mostly on the left, whereas the hole density is mostly on the halides. And so instead of having a uniform charge throughout the whole box, throughout the whole model, we have, I guess, either like a heterogeneous combination. And so we put both charges in the box, but we compute radial distribution functions again. We see that instead of just, you look at the same bonding between the lead and the bromine, and instead of just seeing one peak or the other peak move, you see differences in geometry for both the lead-bromine and the bromine-bromine coordinations. And we even see it in different trends. So for the negative polaron, we saw bond elongation, whereas for simultaneous polaron, we see the bond contraction for this model. I haven't quite rationalized what the difference is, but I would suspect that you have positive and negative charges, so they might attract each other a little bit more. Would be one possibility, but I haven't nailed that down yet. So that's the geometric structures for this. And so you can screen singlet and triplet configurations for both simultaneous polarons. So it's not very labeled very well. So this would represent the whole polaron and the negative polaron in the same model for the singlet and then for the triplet. And if you look at the IR spectra for both the singlet and the triplet, you'll see that the contributions from the positive polaron, they're roughly this, they're pretty insensitive to the multiplicity. So it's the transition energy is about a little less than 0.2 eV for both models. But when you look at the negative polaron for the singlets, it's essentially degenerate, I guess, but closed. So the lowest energy transition is very, very small energy, whereas for the triplets, there's a broadening of the densities states. So the highest energy transition is very bright, and it appears at about 0.1 eV. So the main contribution is that one, the negative polaron is dark, whereas it becomes bright with a different multiplicity. I think that just has to do with triplets. They have magnetic field associated with them, so they can split energy levels. Whereas with the singlets, it's like you have two degenerates and they roughly stay the same energy. You have a triplet, it's like one will raise and one will lower. So you get a little broadening. And yeah, and then the ultimate goal is to move on to do dynamics with this system. But the model is shown to be unstable, so I'm just trying to find ways to get around or to run dynamics and have model knots. Well, they behave well during the dynamics. And so yeah, that's the future direction we plan to pursue further with this week. And yeah, I guess that's my poster presentation.
Okay, but thank you, Aaron. Not the questions. Anything you wanted to?
I guess I have some question about the vibration of analysis. So you said you have some spectator mode, right? But for the figure, I guess I'm just wondering, did you try different orientation of medium? So that maybe the hydrogen pointing towards the bonding. So in this case, you might have some hydrogen bonding. What would happen?
I would still call that spectator mode, because hydrogen bonding is still a physical interaction. So I mean, it would, like if these hydrogen bond, it would make the bonds stiffer.
You know hybridization proton codes.
Right. So when I say, yeah, so when I say active and spectator, active is physically, like it's an actual chemical bond, whereas spectator is just, there's no chemical bond.
Electrostatic.
Right.
So in the top of the poster, you look at infrared absorption for standalone tolerance. In the bottom, you look at absorption of the simultaneously existing tolerance. As it is showing the intensity of the coexisting tolerance seems to be like 10 times bigger. Is it? But you're telling arbitrary units. Are those arbitrary units the same in the top and bottom? Is it an observation that coexisting tolerance give 10 times increase in the oscillator strength?
So the differences in the y-axis are due to how the data set was normalized.
So it is not physical effect, it's just different normalization.
Right.
So you didn't observe a drastic change in the oscillator strength of the orbitals of the similar symmetries.
I guess I can just renormalize all the data to the same number of orbitals. So yeah, I could do that. But I don't remember the oscillator strengths for each individual transition offhand.
Okay. And were you thinking of focusing on the UV visible aspect of this coexisting tolerance? Absorption and emission, and comparing to standard carriers or jointly corresponds to ground state. How much the absorption condition for coexisting polarons, absorption condition in what you published in JAX. Will it be a drastic effect or just with a quantitative correction?
I guess I haven't looked too deeply into that yet. But something, yeah, something I should look into. I guess I just haven't done it because, well, I was just lazy, didn't want to edit the script or edit the data so that I could compare them. But yeah, that's something I could make some figures of.
Let's thank everyone once again. And please collect feedback which may have more questions. The interested you.
So where are we? So the homo state is unoccupied. And the lunar state you put in now. So it should be the same. So it's the same charge with your ground state. So that's the whole. So that's the whole. That's the topology. Red. Oh, here.
Last week I just I completed the network section here. And so graphene has a unique optical properties since it has unusual bell structure. In the Brillouin zone, at each corner, valence band and conduction can touch with each other. At two equivalent points, those are called direct points. At each direct point, conduction valence band overlap, not much. That's why it is called graphene is called semi-metal. And at each direct point, energy dispersion curve is linear. Energy dispersion is linear. Direct point. That's why electromagnetic. So this is the band structure of graphene, and this point Brillouin zone, and this is the zoomed in image of that one direct point. So here we can see that it is a little bit concave. Actually, it should not happen. So I make this quick. And here you can see that there is and graphene has a triangular lattice structure. We consider A. It has three nearest neighbor carbon atoms, and then it has next nearest neighbor carbon atoms. So in the trigonal Hamiltonian, you can see two curves. One for this nearest neighbor carbon atoms, and this second for this next nearest neighbor. So in the absence of magnetic and the external magnetic and electric field, if one solves this trigonal Hamiltonian, the energy dispersion relation is here. For this for deriving this energy dispersion relation, we should neglect this next nearest neighbor apart. We just consider this nearest neighbor, first term, third term. And here K is in 2 dimension, so infinite graphene sheet, two-dimensional infinite graphene sheet. So momentum dispersion is two-dimensional. So K is a function of Kx and Ky. And here it has two components. You can see love functions. Okay, two values actually. And this question is one positive value for conduction band, negative value for valence. And here Fk is now the components of the eigenfunctions of this type Hamiltonian is here with initial momentum K and A sigma. And this is X component and this is Y component. The two-dimensional wave packet is here. There should be one as psi X, why not? And if we calculate the Fourier transform of these two equations, we get eigenfunctions in two-dimensional space. And equation for two-dimensional wave packet in momentum space is here. In the absence of external magnetic field, the Hamiltonian is this one, first one for electron, and this one for photon. When energy is positive, it's for electron. When energy is negative, it's for photon. When magnetic field is present, then the Hamiltonian takes this form, where B is along the z-axis, and there is also the same. We consider on this component, the component of n. By the way, is angular momentum. So this angular momentum in position space has this form, and in momentum space has this form. Now the corresponding Schrodinger equation in the presence of magnetic field is this one.
There a justification to write angular momentum operator in this form, where it comes from.
Justification?
Yes. Like when you go from positions LZ from position space to momentum space. When you replace derivative for position with momentum, dvx with k sectors, it's clearly standard. Isn't standard to replace x with dv official? So here it's not quite visible. The derivative for space is replaced with momentum over x, right? And the Cartesian y is replaced by derivative over momentum. Right? Why? The first one is justified. It's just definition of momentum equilibrium. Is there justification for the second replacement?
Second term, right?
Why? Let one. Y is replaced by t dky. Maybe not immediately, but a reviewer may ask us to explain it.
Okay, so I need to write in details in method.
Or just find it in the literature and give reference. It could be not original research papers, but some textbooks. Okay, sorry for interrupting, please keep going.
It is from commutation relation.
I would say it would come from Fourier transform operators. Yeah. Or class transforms, linear function derivative.
There are two equations missing here. So this one is the time evolution operator. There should be two more equations for the packet, for position and moment space. Here, this one, this the previous figures.
Did you want? Would it be reasonable to put time-dependent Schrödinger equation? Because this evolution operator is used to time-dependent. You show time-independent, and then one can show time-dependent.
Just before this.
Yes, before this evolution.
Yeah. So it comes from time-dependent equation. Okay. And so this figure here we can see the magnetic field values in atomic unit. If I convert these values to Tesla, it's a very big value. That's not realistic. So currently I was not able to calculate for that very small value from magnetic fields. That's why I didn't put this figures here. And this one is
but the figures will look the same way. Can you just explain generally how to interpret these figures and why they need? What do you see there?
Here, this is one of the direct point. You can consider this one as K. And when magnetic field applied to this graphene, we know each carbon atom has one free electron. So when magnetic field is applied to the graphene, so this electron travels in cyclotron because of the Lorentz force.
Can you write it in the explanation to the figure?
Right. And these for very small values of magnetic field, it's just direct delta function. And for at certain value of magnetic field, electron starts moving. So okay. And we can see the electrodynamics.
But if you would do classical magnetism, the center of the wave packet, or no wave packet, the electron with the classical electron would move on the cyclotron in the circular orbit. You see, and here you show the data showing splitting of the wave packet in two parts, or taking more complicated shape. When you go from here to there, instead of moving in circle, it splits into. How do you interpret?
Yeah, since it's two-dimensional.
No, how do you interpret why it splits onto? We start with one wave packet and we end with either two wave packets or something very much broader.
We just consider one direct point, but it should start from all of these 6 points.
why shape of the packet changes. Why it doesn't go as a single unity in a circular orbit. No one knows. We are here to think, not to memorize something and repeat, to analyze and give hypotheses. No one has to. Just try to hypothesize how it looks like and why it works.
Is there any potential failure in these solutions?
Yes and no. It looks like potential error, but it is not potential energy. Kinetic energy was looks the first figure that Fatima showed. It's kinetic energy. Typically, it is parabolic, but is parabolic. And when momentum increases, energy also increases. And here it goes decreases and then it increases again, so it shows profile. And in order to go from one point to another one needs an analog of activation energy. If one wants to go from here to there, if total energy is 0, it cannot tunnel. So it's math of this problem can be very similar to tunnels where they are all just spreading in solid state, spreading over several spatial points. But why it goes two directions? Instead of magnetic, without magnetic field, it just stays here. My Warren's force, it should go one way, and here it goes both ways. But as if electron would have positive and negative charge. Why that? Okay.
And here we can see these figures are eigenstates, different eigenstates.
Uh-huh.
But I don't know for which value of magnetic field.
For the small ones, like
It controls
yeah.
-6.
Mm-hmm.
Yeah, so for these values also, these values must be changed in the next version, and I calculate the corresponding eigenstates. These eigenstates not for these values.
That's fine. What can you tell about eigenstates?
I have no idea.
Like, what could be the eigenstates in case there is no magnetic field?
Actually, electron should be in the ground state.
But when we do GFT, in ground state, we still have orbitals. So it's not one. It's not we're not talking about occupation of orbitals. We are talking about available orbitals. Like, how does the orbital in momentum space look in absence of magnetic field?
So carbon has 6 electrons. Should be p orbital, 3 reaction.
Now we are speaking like a chemist. Suppose we are looking on orbitals in momentum space as function of kx and ky, or px and py. what would be the eigenstates of time-independent Schrödinger equation for magnetic field equals 0?
This is good.
No, time-independent Schrödinger equation. It is second from the bottom of your methods. Yes. So here you have psi as function of kx, ky, and then so your eigenstates in the top right corner are solutions of this time-independent Schrödinger equation, right? With different index. Psi, but they are plotted for some small value of magnetic field. If one removes magnetic field as a reference situation, how would the figures in the top right panel change?
So there will be no magnetic field.
Yes, if there is no magnetic field, how does the shape of orbitals change?
It should be spiral.
So wave function depends only on momentum. If the electron is in the plane wave state with fixed value of momentum, is there any mechanism that will change it? In absence of magnetic field, is there a mechanism to violate momentum conservation?
Yeah, you need to perturbation.
But if there is no perturbation,
External
if there is no external perturbation, is there a way to change momentum without perturbation? Does Hamiltonian permits change of the momentum? No. So if there is a state with fixed momentum, it's a delta function. So all eigenstates in absence of magnetic field will look like this one. It will be a set of individual peaks covering one peak, another peak, another peak, as many states, as many grid points. And then you have slightly different energy determined by this dispersion. Right? But presence of magnetic field induces hybridization between states. And if for substantially high orbitals, they hybridize in the shapes that resemble circular orbitals.
Okay. So first panel is the top panel is in the absence of magnetic.
No. There is a label of states. Yes, it's initial orbitals with low energy. And as energy goes higher, hybridization becomes bigger because of the mechanism that you mentioned. So it's analog of coming over the area. Can you answer? Yes.
Tunneling.
And mechanism similar to tunneling.
Similar, not exactly.
Well, tunneling is defined for potential energy. There is no potential energy.
Tunneling is finding the available state.
If you use the word tunneling, everyone who hears it will assume that one has potential as function of the. But from the point of view of this hybridized eigenstates, can there be a logical connection of the wave packets splitting on two and going in circular orbits in both directions. There should be a connection. Yeah. So if time goes long enough, that any initial state should decompose into one or several of such orbitals. And they do not have preferred direction of rotation. So with time it will end up in circular orbitals. Therefore it goes both directions. So what are your conclusions?
So in the presence of small magnetic field, electron can move in cyclotron motion. But for the big larger value of magnetic field, there should be quantum Hall effect. That is different stuff.
But how do these circular orbits correspond, agree or disagree with quantum Hall?
This circular orbit agree, but the thing is there should be quantized level.
There are those are quantum states with different energies, like quantized, right?
There should be degeneracy as well.
And there is a
multiple states.
Do you check the degeneracy?
For which one? This one?
Yes.
No.
You may.
How to check? I don't know.
Just explore energies of this alien states. And for the conclusions, who needs this work? I mean, not personally, but which industry may benefit from this research?
Up to you.
For which applications? For which applications?
When electron travels, it the direction changed in its direct point, and the velocity is lower, speed is lower, and then it is benefited for having photovoltaics.
What is the connection to storage of information? Yes. Quantum information qubits.
Oh, well, for bigger values of magnetic fields, there should be quantum Hall effect and lambda levels. Those lambda levels can carry quantum information.
Excellent. You may mention the conclusions.
But there is no, we are not considering lambda levels.
How much these circular orbitals differ from lambda levels?
For lambda levels, we need to solve the Dirac equation instead of Schrodinger equation.
You may write these observations from this point of view right in the post. Like it is not quite lambda level of the post, and then explain your point of view.
That's all.
Okay, but thank you. Other questions? In addition to it. Okay, yeah, but thank Fatima once again. Please collect the feedback if there was some. Okay, and Kevin is invited to go over the poster.
All right. should I pretend that the people at this symposium know what non-adiabatic dynamics is, or should I explain it to them?
You better explain. If
Okay.
they know, they will stop you and ask to go forward, but it's better if you give introductions.
Okay, so non-adiabatic dynamics is essentially this equation right here. So non-adiabatic dynamics is as follows. In the regular classical adiabatic dynamics, you have a nucleus and an electron. So as an electron gains energy, it jumps into higher orbitals. But however, the fundamental assumption we make is that the nucleus's position doesn't change in time. All right. So any like expectations we calculate when that electron returns to its ground state in the adiabatic approach is zero, because nothing is changing in respect to time. However, in a non-adiabatics, we're assuming that the nucleus is moving in time. All right. So if that happens, then the orbitals are going to change. Okay. So an electron moves up into higher orbitals, but when it loses energy and returns to the ground state, it's not going to be the same initial ground state. So the expectation values are going to be non-zero. All right. So what I'm computing are the electronic relaxation rates. Using non-adiabatic dynamics. Basically, I'm studying how long it takes for electrons to return to the ground state in the non-adiabatic approach. All right. So these are all the orbitals and orbital holes I looked at using non-adiabatic dynamics.
Wait. Orbitals and dynamics, how are they connected?
I'm studying the orbital transition rates using non-adiabatic dynamics.
Okay, but orbitals have their shapes independent of your research on dynamics. You need just optimized ground state, and then you can find orbitals.
Okay.
Right?
Mm-hmm.
So it was sounding confusing.
All right.
So you see what in your methods, there is a little change in the structure. So equations that you provide are related to dynamics, right?
Right.
And then later you may add observables, but before that, you may add a couple of words, a couple of equations on ground state DFT.
Okay.
And orbitals are results from just ground state calculations.
All right.
Okay, keep going.
Okay, so I calculated like electron relaxation rates and relaxation rates for the electron hole. I calculated expectation values for the energy and position, which you can see there. So using FOSP, I calculated my non-adiabatic couplings, and then using some MATLAB code, I calculated the relaxation rates, and then I plotted these graphs right here just to see how the electron relaxation rates would vary with the temperature.
You're going too quick.
Okay.
If I'm hearing for the first time, you told about non-adiabatic dynamics, how orbitals change in time, this is fine. And you didn't explain your green and blue panels. It's a little, how to say, I'm not telling, nothing is wrong, but humans are very conservative. And if you jump between subjects too quick, it may surprise too much.
Okay.
Just a little slower. We talked about dynamics, and then tell what is shown on the figures as they are aligned. Go from top to the bottom slowly. So before decay constants, you may explain what are green and blue diagrams.
All right. So these green diagrams, I'm basically studying how the excitation value for energies changes with time. So each of these graphs are for different orbital transitions at the different temperatures. For example, this graph right here is from HOMO to LUMO +7 at 300 Kelvin, and so on and so forth. And then from these, I computed the electron relaxation rates and the electron hole relaxation rates. All right. And then these blue graphs right here are the position versus time. So here I have my diagram of my lead telluride nanowire. Right here, you have some iodine dopings in the top section here, and then some sodium dopings in the bottom section right there. And then I'm seeing how the expectation values for the position of the electron and the whole change with time. So as you can see in all these graphs right here, all the movements are localized in the iodine doping area right here. There's no movement in the sodium doping over there. And then by studying these position expectation values, how they change with time, I came to the conclusion right here that temperature is directly proportional to the rate of migration. All right?
Wait.
Oh, sorry.
So, in your blue figures, which it looks like you explained them with enthusiasm, is there a relation to charge transfer? Can one extract information about charge transfer from your blue figures?
From studying these graphs, you can say that temperature is directly proportional to the rate of charge transfer.
I see what you're saying. You're making a very big jump to immediate conclusion.
Okay.
If someone will ask you to squeeze your poster in 30 seconds, you can do it. But if you have more time, give more details. It would be interesting. So, one comment. Another, it would be very unusual to say temperature is proportional to rate of charge transfer or energy relaxation. Same as in your major is physics. You cannot say that voltage is proportional to current. If a meticulous teacher will lower your grade for such saying, you need to say current is proportional to voltage.
Okay.
So you need to, in your verbal construction, you need to specify what is the source, what is the origin, and what is the consequence.
All right.
So it would be much more correct if everything your correlation is correct. The right verbal way would be say that charge transfer rate is proportional to temperature, not otherwise. For some people who like logic, it will be very unusual and very confusing.
Okay.
The temperature is source, rate of charge transfer is consequence. But before we are going to this conclusion, how to interpret your blue figures, we partially covered it, and how are they like? What is charge transfer?
Charge transfer is essentially the rate that electrons move from one place to another.
Okay, good. Other solid and dashed lines on your blue figures.
So the
Yes or no?
yes,
Okay, what do they mean?
the dashed line is the expectation value of the electron position.
Good.
The solid line is the expectation value of the electron hole.
Okay, so if your definition of charge transfer is moving of a charged particle from one spot to in location in space to another location in space, if your dashed and solid line are parallel to x-axis, would it correspond to any charge transfer?
No.
So then how would you formulate criterion of charge transfer?
The charge transferred would be the derivative.
Or just, yeah, correct. Or visually just observing that this dash and solid line change in time.
Okay.
For example, if they intersect, it will be ideal charge transfer. It means electron and hole swap their space.
All right.
So you can introduce it verbally and then go over the figures and show which of these figures show the best charge transfer.
Okay.
Can you do it right now?
Sure. So, for instance, at this transition HOMO to LUMO +7 at around 300 Kelvin, you can see that the electron there's very little charge transfer displayed for that temperature. However, as you study this orbital transition for higher and higher temperatures, you see that that the electron position change with respect to time is greater. So you can see here, as you study this orbital at higher temperatures, that the charge transfer changes.
Earlier in time.
Yeah.
Means quicker. Good, good. Okay. Another question that you may jump over, but it's is there a difference between relaxation of charge and transfer of charge? It's basically a question about difference between blue and green figures.
Okay. So for one, relaxation of charge is the time it takes for an electron to return to its original ground state.
Mm-hmm. Okay. And the same. Okay. And the charge transfer you already described. Mm-hmm. Is it possible? Is not necessarily for your system, but generally, is it possible that charge relaxes but doesn't transfer anywhere?
That could be possible.
Yes, and therefore you need both blue and green figures, because green figures with relaxation will always show some dynamics, but maybe there are situations when energy of charge changes, but position of charge doesn't change in space.
Okay.
So blue figures are more representative for charge transfer. Okay, and now, if you want, please go forward to the rates.
All right. So then I made a graph. For example, this graph right here shows how the decay constants for electrons change with respect to energy difference. So I took the natural log of the electron relaxation rates and then studied how they change with energy. Yeah, sure.
So it is not clear, if I assume that I never saw this results, it's not clear where the decay constant come from. Even if you want to be very brief and skip details, is there any connection between green figures and your decay constants?
So the decay constants is essentially, from what I remember last week, is just the derivative of this dashed line, which is how the excitation value for the electron's energy changes with time. It's just the derivative of this dashed line.
Excellent, excellent. Please consider to add this protocol as a formula into observables.
Okay.
And now an important form for your verbal presentation. Would it be correct to say that you have many green figures, and from each green figure you get one data point in your decay constant?
Right.
You didn't tell it. You need to tell it.
Okay.
Like you summarize this two-dimensional complicated figure into one number with a specific algorithm and specific formula. And then it will be much easier to perceive what you're delivering.
Okay.
Please keep going.
All right. So as you can see here on this graph, in the lower temperatures, there's hardly any change with respect to energy. The slope is really low. However, as you go into higher temperatures, you see that the decay constants change with respect to energy becomes much greater. However, if you look at these decay constants for the electron hole and you see how they change with respect to energy, the change is almost negligible. And I'm not really sure how I got this large slope for 900 Kelvin. Maybe it was just a fluke. So from my results, I conclude that the Van Gogh law applies for electron at high temperatures, but not for the hole. So that's my conclusion from these graphs. And then, Professor, you suggested that I make these graphs just to explore how the electron relaxation rates and electron hole relaxation rates change with temperature. To me, it doesn't seem that there isn't much difference. I mean, for these data points, they almost overlap. They're practically, you could say it's like practically the same data points. Mm-hmm. So it doesn't seem that to me that there's a much change in temperature for the electron, but for the electron hole there might be a little bit of a difference. But again, I think it seems to me like about 60–70% of the data overlaps with this for this electron hole relaxation rates. Mm-hmm. So I don't know. My conclusion from these two graphs is that the electrons relaxation rates don't change with respect to temperature.
Well, they all change consistently in the same measure, independent, with very low dependence on initial excitation energy. The dependence on temperature is very similar.
Right.
Okay. Can you point your hypothetical gap law in your introduction? Okay. So what is alpha?
Alpha is a constant. It's just 1 over energy.
What? You sure?
Okay, so whenever you're taking the exponent of something, this argument in here has to be you know this, right?
Okay, so alpha, dimension of alpha is 1 over energy.
Right.
But what is the physical meaning of alpha?
Alpha is can you give me a hint?
Yes. What is the connection between alpha and temperature? And Boltzmann constant.
Okay, so I'm guessing alpha is just 1 over temperature, and this alpha right here is just 1 over k sub b?
Yes, alpha equals 1 over kb times temperature. Right?
All right.
So if you plug it explicitly into your hypothetical expression, then it will show how the rates of your electron transfer should depend on temperature.
Okay.
So and you can plot this hypothetical rate on the same panel where you showed data.
All right.
And look, tweak a little bit parameters like by feeding procedure, and look if your hypothetical dependence of the electron transfer rate on temperature would approximately fit these data points.
All right.
Because it seems very reasonable. When temperature grows, the rate increases, and maybe you already have it in your equation. And if your hypothetical equation and numerical data, at least qualitatively, agree, it will be, I wouldn't say greatest discovery of the humankind, but it will be an important step forward for these materials. It's possible?
Yes.
Very good.
One other comment I just want to make. You guys said that there might be something wrong with the 500 Kelvin and 700 Kelvin data. So I went over and looked at it today, and to me there doesn't seem to be anything wrong with that data. To me, at least, that doesn't mean I could be wrong. So if you guys really think I should check it again out, I can check it again, you know.
Okay, let's thank Kevin. Other specific questions you want to please him with?
Why do you need dopants?
You need dopants to modify a material's electronic properties. I guess so specifically in this case, it's to increase the magnitude of the thermoelectric effect, because if you didn't put any dopants in there, the charge transfer rates would be really small. There would be almost like no charge transfer. But if you introduce dopants, the charge transfer effect rates would be much greater.
Perfect. I don't know, as Aaron, I'm 200% satisfied.
So with P and N dopant supply, so is iodine like a P dopant? So it's positive charge and sodium's a negative?
All right, so my periodic table, iodine is on the right side of the periodic table. So iodine would just need one electron in its outer shell to be a noble gas. So I'm guessing it would be an N junction.
But definitely, iodine and sodium are opposite dopants.
Right. So one add the charge, one remove the charge.
All right, sodium donates one electron because it only has one electron in its outer orbital. It donates one electron to iodine.
So iodine is your P dopant. So P is positive charge. And then N is dopant. So sodium gives an electron.
Right.
It would be, so that'd be like your N. Yeah.
Did you write it down?
I just wrote why are dopants needed.
Okay. Kevin, remember you were taking the course Computationa Chemistry and writing a report?
Mm-hmm.
And in your final version of the report, there were some comments identifying which is which, and maybe some chemical equations for those. You may copy paste them into the post.
All right.
This consideration. Not much words, but like a couple of who loses electron, who donates electron. And as a continuation of Aaron's question, I want to ask more. the nanowire is composed of lead and tellurium. Which of them is replaced by iodine and which of them are replaced by sodium?
So lead is replaced by sodium.
So, okay.
Right, so
Uh-huh,
I'm
uh-huh.
not sure if I'm right. So if I
Yep.
remember, lead has like I think 2 electrons
Mhm.
in its outer orbital, so
Mhm.
it gives 2 electrons to telluride.
Mhm.
So since sodium also like gives electrons, I'm
Mhm,
assuming sodium replaces lead. That's my
Yes.
understanding.
And iodine replaces tellurium.
Right.
Excellent. You may mention it explicitly in your poster because there will be no experts who literally do the systems, and even for smartest people, it takes time to perceive what is being done.
Okay.
And these basics are very helpful.
Got it.
Next question. Any more questions or suggestions? Or maybe a suggestion where, from your opinion, is the weakest part that needs immediate attention? Like if there is a lack of time, what should be fixed in the primary?
The Excel figures. I would just plot them in not Excel,
Okay.
like something I just looked.
Is MATLAB okay?
Yeah, man.
For me, yes, I don't know about early.
Yeah, it would be fine. I guess, I don't know. It's always, Excel figures are always not the prettiest to look at.
All right.
Did you mention it in writing?
I did not.
So the origin is good.
Huh?
Origin.
But I do not have license for Origin. You know, if library has or Kevin has private license. Origin is great, but it's commercial.
Any other questions?
If not, let's thank Kevin once again.
Thank you.
So many thanks for helping each other. Kevin, please collect the feedback from the groups. Thanks much for investing time. Next Tuesday there will be last dry run. So please try to bring almost perfect versions of the posters that will need minimal changes. And printing will be arranged on Thursday, so I can basically the day after the event will be. And we will have 5 instead of 3 posters next time, so it will be less time to present them and fix some glowing errors. So try to prepare it to a perfect shape as possible.